Morning all. Is Yaka? Yeah, Yaka said I'm presenting on behalf of Richard Novik, who for medical reasons couldn't turn up. And so excuse me if these questions, please let me know. If I can't answer it, I'll take the note and get back to you on that. So what the topic today we're talking about is thickness testing using ultrasonic method, the accuracy and repeatability of that. Well, how often do you hear the comments of the material seems to be getting thicker? We got it up and thickness was way out. The last guys didn't know what they were doing. They didn't find it, and they should have found this. And also, I hear some comments of, what am I doing? You know, am I doing the right thing? Just all these questions that get asked. So, what's the problem with the thickness measurement? Deceptively easy. Complex interaction of sound material, sound in the material. What happens to this sound inside the material is how well do we understand that to determine what happens with it. That's one of the most critical things. The material geometry, the surface condition, the structure, the temperature and the coating. Probe selection, very important. I was talking to someone earlier on and saying, you know, most of the guys we walk around with a thickness gauge, think a 5 megahertz, a twin crystal probe in the pocket will do it all. Unfortunately, it doesn't. So there's a whole lot of probe selection that you need to be able to determine the corrosion, typically with the material that you're using, and the thickness as well. So probe selection is quite critical. The detection technique, even on simple thickness testing, there's a couple of techniques that I'll tell you about that determines how and where to use that type of technique. The measurement technique as well, mainly to do with surface corrosion or surface coating. And then the most important of all is the operator training. How competent or how good is a person using the gauge or the instrument that can give you the results. But not all corrosion behaves the same, and some can be hard to detect and measure. Picture of a general corrosion, it's quite heavily corroded. What we call in the non-destructive testing industry, the MIC, microbiological induced corrosion, and then there's this, pits. Now with the pits, they can be localised pits, which sometimes can be a little bit easier to work with, but if it's a scattered pit, then yep, it's going to be a challenge. Right, the basic ultrasound theory, what you put in is what you get out, it gives you the result. So you want sound into the material and sound back out, and in accordance with that, you get the thickness measurement. Now, these thickness gauges, which will just give you so these thickness gauges, which will just give you a thickness reading, but how good is it reading? You wouldn't know till you have this ultrasound A scan, what we call, and that is amplitude versus distance or time. Now, distance is measured with the formula of velocity times time divided by 2. That's what we use in ultrasonic terms. These are obviously distance, the material velocity, and the time. All right, probe type. Corrosion surfaces tend to scatter sound. There's two types of probes that we use, a single crystal and a twin crystal. For generalized corrosion testing, single crystals not ideal. You'll probably get about 5% of work done with a single crystal. Reason being, this sound that comes in, you want that sound back into the crystal so that on the thickness gauge, when it goes to the gauge, you can get a scan of that plus a thickness reading. But when your back wall is so heavily corroded this sound signal scatters all over the place, and these minimum sounds, if that, if it's any of that, this type of corrosion, you're not going to get any signal back. It's just so heavily corroded. So, what do you use instead then? Twin crystal. Twin crystal is a roof-angled transducer. So you've got one side is a transmitter, the other side is a receiver. What the roof angle and the focus gives you is a higher probability of detection. So this actually allows signal to be captured by the receiver or the receiving crystal. Twin or dual crystal probes are preferred probes for most of the corrosion thickness testing, or I would say probably in general, all corrosion thickness testing. Right, instruments. What instruments are used? These specialised flaw detectors. And when I say flaw detectors, these things can be used for 90% of the application for these instruments are for weld inspection, testing the weld integrity, looking at different type of defects in the weld. So you can use ultrasound thickness testing using these instruments or the specialised thickness gauges and that there. So this particular unit is what in the industry people call a D-meter. It's just a digital readout, and all it does is gives you a thickness. But what we strongly recommend is if you're doing any thickness testing, unless you're in a quality control environment, then this will be okay. But if you're doing any corrosion testing, you should have an A scan to refer to. It gives you far more information than just a thickness. Otherwise, it's thinking of what's happened, where's my signal? Because there'll be a growth in here if it's not coupled properly, right? So instead of reading 7 mil, it's reading 7.3 mil. So where did the 3.3 mil come from? Or you will have no signal because of the heavier corrosion. So is it I'm not coupling properly, or what's going on? So that's why the A scan is so critical, because it gives you far more information. All right. The errors that there are during the thickness testing process, one of them is in calibration. Calibration is the process of converting time to distance. Velocity is distance in time, constant of for a material. So here's a picture of the that shows your distance in time and how you can correlate that. Now, 0 point adjust for crystal not being right on surface and electronic delays. By measuring two known thicknesses, a calibration is achieved. So what this statement says here, by measuring two known thicknesses, the calibration is achieved. We calibrate to a zero crossing here, which is the minimum point, minimum thickness, and then we calibrate to the velocity here. And once that is done, we get the 0 point here, which automatically is set by the electronic gauges itself. Still on the error, on the calibration error, velocity for calibration piece must be the same. I've gone into places where people are using carbon steel calibration piece and they're actually testing stainless steel. You can't do that. The material is totally different, the velocities, the structure, the grain structure is totally different. So you need to calibrate to the material that you're going to test. So if you're testing carbon steel, you need to calibrate on carbon steel. Right, so the calibration piece dimension accuracy is very important as well. The test range needs to be between the thick and thin calibration. So if you're calibrating, I was going to get a step wedge, I forgot about it. So what we generally supply to the industry, or the industry experts have, is calibration pieces, multiple calibration pieces, aluminium, carbon steel, stainless steel, and probably stainless steel of different grades as well. So they have a step wedge. So you calibrate between, say, 5 mil and 15 mil. So that's your working range. If you all of a sudden calibrate between 5 and 15, you take it up to a 20, 25 mil, your level of error is quite high. So this is where this statement comes in, that your calibration needs to be between thin and thick pieces. Coupling, very important. How much? There's never enough couplant on the surface, so lube it up and you use as much couplant as you want. Doubling can occur when calibrating thin parts and where the transducer is worn, so I'll touch on these a little bit later on. And then zero offset errors in calibration. So what the zero offset errors actually mean in calibration is this bit here. When everything's perfect, the zero offset's minimum. When the probe's worn, you've got a bigger offset here. When it's convex or concave shape or uneven shape, there you are, your errors, zero offsets there. And again, in heavy surface corroded areas as well. So what is doubling? Doubling caused by detecting the wrong signal to measure. Mainly with thin samples, first echo is not the largest signal. And here's an example of doubling. What happens in the twin crystal probes is the transmitter signal comes in, looks at the front wall of the crystal, fires it back into the material, and that signal goes in here into the receiver. So you've got this signal going in plus the reflection going back in there. So two signals, and that's what is doubling, and that's what it shows here, the doubling effect. So generally this is that signal there, and we normally would be looking at around here for your actual thickness. Right, causes: transducer focus point, transducer wear. Solution: increased gain, so correct signal can be detected, but you need to know a little bit about the what we call this graphical representation of a scan. Gauge will read correctly on thin and thick calibration piece, but will be non-linear in between. The next error that we normally face is the measurement point. There are generally three ways to measure distance: peak, flank, and zero crossing. So peak measures the highest point on the signal and can be done on most floor detectors. Right, so the peak signal is when there's a gate on the floor detector, and under the gate is where above the gate is where the peak signal is, and that's where the measurement points are taken from. Two high points can happen in twins on a certain situation, which is the high point when multiple signals can cause can't measure when signal saturates or is too big, therefore not commonly used for corrosion. Flank. Right, flank measurement. So gate set to detect minimum signal, usually set to avoid noise. So what happens, just going back into peak, so if we were measuring off peak, then this is the gate, this is signal. So the peak signal will measure from here. Anything above the gate is the measurement point. That's what peak is. Flank is right where the gate is, right on the edge of that signal, the rise of that amplitude over here. So if this gate was up here at about 40% screen height, so the measurement will be taken from that point there. Gate position and length set to cover thickness range of interest. Gauge automatically determines thickness where gate cuts weigh. Lower signal equals thicker result. Right. Error from flank technique. Calibrated at 10 mil, higher level signal, and the signal's saturated, and you calibrate it at 10 mil, and that's gone right up there, or you've lost a couple of 0.2 of a mil, and then the next thing there is when your signal's not high enough, and you've got 0.3% gain in there. in the case of typical pit, you've got much more or less a signal there, and your error message or error percentage is higher there. So detected 10 mil signal measures between 9.8 to 10.5, and that's a problem with the flank measurement as well. Right, zero crossing. Right, best result option: zero crossing. Noise and multi-lobe signals make it difficult electronically. Requires signal processing software. Only available on thickness gauges, floor detectors with some corrosion modules. First signal detected at 20% screen height is captured. Zero crossing point is determined from captured signal. Repeatable accuracy regardless of signal level. Can miss small echoes from bits, etc. Should use waveform to check result sensitivity. So what is this zero crossing measurement? So you're calibrating there at 10 millimeters. Your high level signal there is still at 10 millimeters, even though you are oversaturated, you've got no peak indications, but this measurement's still 10 millimeters. And when your measurement's really low, you're still measuring 10 millimeters. So what this actually means is it's reading off the back wall, the first back wall of the signal, and anything, the measurement point's taken from anything which crosses 20% of the screen line. Okay? So you can't really see the grid there, but it's about 20% there, 40-60, and that's 100% screen line. So the standard result of entire signal range above 20% screen height detection point. V-path error, calibration over a large thickness range. For example, a 5-step wedge calibrating, a 5-step wedge which is 1.5 inches down to 0.05 of an inch. Calibration done between 1.5 to 0.05 inch. So your V-path error at 1.5 inches is nothing, and then down to 0.05 of an inch is nothing. But in between, you've got of all these other steps. So in between of all these other steps, the 3/4, 1/3, and 0.15 inch, you've got quite a significant error in here. Now, to some, it's not that critical, but depending on your procedure, your processes, it can be quite important of how much wall loss that you have had. So, cause sound path is not 0 degrees; it's roof angled. Angle set by a probe, roof angle. Calibration sets start and finish points. Points in between not linear. Solution: minimize error by using a smaller thickness range. So when you do come into a situation like that, so the best will be to knowing the current material, what the thickness range it should be from new to what your tolerances are, then going back in here and maybe using 1, 2, 3. So using the 3/4 and 0.15 inch as your 2 calibration points instead of having such a wider range to get your accuracy levels higher and your errors lower. Built-in V-path correction, thickness gauge, only recognised probe. So there are systems out there, the thickness gauges out there where it has auto probe recognition. So all these V-path corrections been set up in there. So it's pretty much a plug and play. All you need to do is just verification on thickness on step wedge as to you are within the limits. Some thickness gauges, custom V-path building for probes. Right. Next error is surface coating. Paint coating usually around half the speed of steel, takes twice as long through steel. 0.5mm coating adds to more than 1mm to steel thickness measurement. Significant error opposed to all first echo thickness measurement. Often variation in coding thickness. Calibration with coding results in all readings being incorrect except cal points. Foam-like coding. So when the coding's, most of the time you can look at the condition of the coding and say, if it's good coding or not. And one of the typical things we do, or the industry guys usually do, is rub their hand on the coding. And if you feel the chalky coating or the paint on your hand, you're not going to get through it. So you might as well just take the paint off and then measure. Right, so coating's quite, the condition of the coating is quite important as well. Right, solution. Measure from echo to echo. So you're measuring from the first back wall to second back wall, or second to third back wall. I know the refinery, they measure from the second to third back wall, not from the first back wall, just to eliminate if there's any other interferences or any other type of ultrasonic waves that could interfere with the reading. So I'll show you what the first and the second back wall echoes actually do look like. Use special through-go probe technique. So what the through-go probe technique is, it's these specialised probes with the correct software that eliminates or accounts for the coating thickness, and you can then measure the coating and separate it from the parent material. Right, error reading with coating measurements. First measurement, right? So reading without coating, 10 millimeters. There's your coating, just a little credit card that Richard actually was trying out. So now from the first back wall echo, instead of reading 0.8 millimeters on the card, so which should be collectively as 10.8, it's reading 12.1. So that's about 20% error there. Echo to echo measurement. So what the echo to echo measurement is, this bit here. Right, so that's your first back wall and that's the second back wall. So you're measuring from there to there, you're eliminating any coating in there. So at the moment that's got no coating, this has a coating, and the indication of the coating is right there. Right? So we're eliminating that and we're measuring from there to there. So first to second back wall echo, and like I said at the refinery, they measure from second to third back wall echo. And why do they do that? To eliminate this. If this was significantly high, you could be taking a reading from that, and also to get rid of all these other mode conversions. So these are different speed of sound or ultrasonic velocity. Right, echo to echo eliminates coating and coupling errors, higher accuracy. Echo to echo is the most accurate measurement technique. Eliminate zero position errors. Right. Problems. There's always problems. Echo to echo, issues with that. Right. What happens when it's heavily corroded surface, or the back wall is heavily corroded? Like the first picture that I showed you, you're not going to get a second back wall echo. So what do you do then? Right. Scatters the sound. The second back wall echo, which is about there, is just too low. You can't use the echo to echo in that situation. Common situation. Increase the gain. Increases. If you increase the gain, all these will increase and come up here, and then all of a sudden you'll be reading from there, right? Because that becomes 20% of your screen height. Coating attenuates signal to make it, the situation even worse. Noise and other signals, example mode conversions, can cause false readings as well. So what do you do through code? With the first back wall echo, what we do is we use the through-go probe, and that measures from the first back wall echo and separates the coding as well with the correct software and the correct probe, as you can see here. We're not measuring from echo to echo, we're measuring straight from the first back wall. Here's the coding, here's a coating reading, and we're reading off that. So I mean, there's a little bit of change here. Probably Richard didn't calibrate it with a coated material, and hence he's got 0.04 mil extra in there. Special probe, softer determines end of coating. No error from coating can give coating thickness, needs calibration or high level of accuracy. Works without coating too. So with this probe and software base, you can use it in general corrosion, but when needed, when there's a coating situation, then you can just select the coating option and use the through coat measurement. High corrosion situation through coat. Again, you've got a backwall, right? So even if you increase, even if this backwall was quite low, you increase the gain on that, it's still be reading off that as long as you can have better control of that and keep it below the 20% screen height. So here we are reading the coating, reading the coating and your thickness. As it says, only need to detect the first echo or first backwall for accurate measurement. So as you can see here, this is what the clean backwall will look like through coating. Right. Other sources of or means of error is surface condition, flaky, chalky coating, uneven pitted surface reduces the signal, will give thicker results than true. The shape convex, you know, your contact area for the probe is too low, so you've got less sensitivity. Concave surface, you can't even see the probe on it, so you're not going to get anything back. Reference thickness as well, on reference plates especially, or even pipes and tubes, just knowing that how repeatable is that reference plate or reference sample for you. You know, how even is the thickness on that also determines your accuracy or error levels. The location, repeated measurements get very different results even from a slight change in position. And last, the operator. Very, very important. A well-trained operator to understand what he's seeing and what the readings actually mean. Right, isolated pits, MIC, which is the microbiological induced corrosion and similar. So spot testing or scanning are not reliable ways of detecting these. The best approach is using corrosion mapping. There's different techniques there for corrosion mapping that you can use. After location, measuring remaining wall thickness may require a separate measurement process, best done by an NDT professionals. Conclusion, there are many sources of error, most of which can be controlled. Some of these errors can be very significant. For general corrosion, most consistent results are obtained from a zero crossing based thickness gauge. Some floor detectors have corrosion modules, usually as an optional. And away from display is essential for all thickness measurement, plus the operators. And that's it. Right.
Any question?
Okay. So I'd say probably temperature as well is the other thing for probe selection.
Yes.
It's probably not on there. That's probably really
true.
key.
Yes, it is. Temperature is quite critical as well. Yeah. I think there is. Sorry.
So I had two questions. One was really around a specialist sort of coating situation. So depending on who you talk to, you get different answers around managing thermal sprayed aluminium external coating. Any key differences you would see in terms of probe selection or method for like a thermal sprayed zinc or thermal sprayed aluminium compared to an organic, or really just the same way of managing it?
No, there'll be difference. There'll be difference. Yeah, absolutely.
Anything in particular that you sort of look for?
See, in some of those difficult situations, what we can do is we can try different techniques or methods and then come up. these, like I said, there's no one particular probe that can do it. Even with these encoding software in a specialised probe, but that's based on the properties of plastic or plasticky type coating. But when it comes to the aluminium type coating, or slightly different, then there's obviously I don't think the coating software will work. We'll have to probably work through the Echo. But there'll be some testing that will need to be done.
So you're qualifying. And the other one was, as funny enough, sort of picking up from the PFB discussion we had earlier this morning, one of the solutions we use for assuring against corrosion under fireproofing on vessels is obviously doing the internal scan from the inside. One of the complications that comes in there is some of our vessels are internally stainless clay. So calibrating for a stainless layer to carbon layer to actually pick up the back is what we're actually looking for, which gets really
Quite tricky, isn't it?
Yeah, something you've had experience with, or
Not particularly myself, but Richard, the guy who was going to present it, he does work on.
So you work.
Yeah.
I was encouraging you not trying to attempt something that's impossible.
Have you spoken to any of the entity?
We're working on qualification of it.
Yeah, okay.
Or just general feedback.
Yeah. So, I mean, if there's anything that you want me to get some information onto you, let me know, and I'll get Richard in contact with you. Thanks.
Is there a minimum number of tests you need to do to be accurate?
To be accurate?
Yeah, like, do you have to do a certain number of tests in an area to get?
I mean, not really. I mean, your accuracy level comes to pretty much the calibration process, and then the operator as well, as to how accurately he's calibrated the device to be able to do the measurement. And it comes down to that. I mean, obviously there's a little bit of like Reese pointed out, something you missed out was temperature, and these other conditions as well, and so that adds to it, I should say.
So I'd say there's accuracy and then there's repeatability, right? So accuracy, I 100% agree, but we read a number of trials many years ago. We were specifically repeatability with common step blocks, common materials, and variation of operators, and we carry out on the very best day with the very same thing side by side, we would give no more than a plus or minus 0.2 on repeatability. We carry that error as a starting point on that basis, and that was because when we did a statistically significant sample using all the other variables controlled as much as we could, we still saw that type of scatter. So it's a bit of a rabbit hole if you want to go down it, or you can just carry a penalty. There will be readings for it. So.
In Australia, NADA's actually released in June the technical note relating to statistical uncertainty of measurement. So anytime you record a numerical measurement, you also need to record that statistical uncertainty of measurement. It's not something that's being enforced in New Zealand at the moment, but it will come. So good luck.
Yeah,
Because it's got huge ramifications with compliance because it doesn't just apply to thickness.
Well, I think it's going to come to that part of it will be come to New Zealand really soon, especially with irons. I mean, not part of NADA, but accepted by NADA.
No matter of but it's definitely different from order of accuracy in terms of the inherent restrictions of the physics within ultrasonics. It's more about statistical uncertainty of the measurements.
I think it'd be fair to compare a thickness tester with a violin. In that relatively, it's as good as the operator that's using it. And, in 30, 40 years, the market seems to think, I don't mean you folk here, I mean the general industry, you go out as a marine surveyor and you look at pitting on a hull and it says, how deep is it? And we'll do it with ultrasonics and say, no, drill a hole and you know how deep the pit is. But people seem to think that they can take an ultrasonic thickness tester and measured the depth of steel at the bottom of the pit. And, you know, I think there's an educational requirement of the general industry, so I feel for you. I mean, in cathodic protection, we used to be known as the black art. Well, I think it now belongs to you folks, and we've now grown up a bit. But it certainly, it says a lot for the operator that those who are very well experienced will give you the best results.
Yes,
And you get
absolutely. Absolutely. I mean, in this presentation, Richard has pointed out, I think, 3 different places, right at the end, operator, trained operator, understanding what he's doing. You know, there's a whole calibration process, and then the signal that you see, you know, what does the signal mean? What am I doing, you know? And there comes the first slide, which had all the comments, you know, what am I seeing? How come there's a growth now instead of reduction in thickness, you know? So all that, yeah, trained staff, very critical.
Faizal,
Thank you.
Yeah.